Hey dude, I got a cool example for using a BJT as an amplifier. We're amplifying current. And specifically we're amplifying the brightness of a light bulb. And it's actually a pretty neat light bulb. It's a 60 volt light bulb. So it's a light bulb that you would put in like a spotlight. That's pretty cool. So what we're going to do is we're going to vary the brightness of the spotlight with a potentiometer. Okay, we've got a voltage divider circuit here. I'm going to walk through that later in the video, but right now I want to focus on kind of, because this mirrors the assignment, what you can do for your assignment, because your assignment has a motor, and then I think it's got, whatever it is, it's got a varying voltage coming in from some kind of sensor. I forget. So here we go. What we're looking at here is we're looking at a circuit, and I want to talk about why I chose this guy, and then maybe go into gain a little bit, and what gain do we choose? Okay, here we go. So I chose this particular transistor because it can deal with a very high voltage from my CE. It can deal with that no problem. Now the current that it can handle is way more than I need, but it's okay. We're focused on dealing with the fact that it can handle 60 volts drop across that. Okay, so let's go through looking at the transistor before we actually do the math. Okay, I'm going to grab my sheet. You can take a look at that. Okay, good. So in my sheet here, this is actually a screenshot straight off a DigiKey, and that's actually what the transistor looks. You can see it's a surface mount. Okay, so if you look down, you can see that the CE can be up to 80 volts. Because I want that, because at some point, my CE from here to here is going to be 60 volts, because when I turn this down, that's what I'm going to have here. When there's no current going here, I'm going to have a voltage drop from here to there of 60 volts. So this thing can handle 80, so we're good. Now, as you can see, it can also handle 2.5 amps. That's a big deal. We're not going to need all of that, but that's okay. Cool. Now, one thing I just wanted to talk about is this guy, 0.3 volts. When I go to the data sheet, this is actually a screenshot from the data sheet. So if you take a look at it, we can see the collector emitter saturation voltage, when it's saturated, is going to be between 100 and 300 milliamps. What I want to go with is, I'm just going to go to the 300, just for the heck of it, because it doesn't really matter. When I calculate that at 300, I'm good, because I've got 60 volts here. If I lose 300 across here, millivolts, doesn't make any difference. I still get the same amount of current through here relatively. So I'm going to go with 300 millivolts there. Now the next thing is, take a look at the gain. This is where it gets a little funky. Okay, so this is just a screenshot from the data sheet, and if we look, we can see the gains. There are different gains for different temperatures. Obviously, the really small one, minus 40 degrees Celsius, we're not going to touch that. But the next one, 25, and then the one up from that is 75. So I'm assuming that we're going to try and keep this thing at a basic, simple temperature, as kind of cold as we can get it. Depends on the environment that it's in. If it's in a box and it's all tight in there and you don't have a heat sink on it, it's going to get hot. So you want to put a heat sink on it, and you also want to ventilate it and allow it to get warm. So I'm assuming it's going to go, I don't know, we'll keep it under 40. So it's maybe not going to go all the way up to the next gain up. So let's just take a look. I'm just guessing maybe a little bit more than, it looks like 250, a little bit more, 280. So somewhere in between 250 and 280. And the reason we want to choose that gain, why we don't go with the minimum gain, is because we're not doing BJT as a switch. We're not saying, okay, I'm just going to saturate you completely. The BJT is fully saturated. Whether I try and saturate it a little bit more or even a lot more, it's not going to change the nature of how the load is running. But in this case, we want to actually balance the load. We want to control the current through the load. So we want to actually make sure that we don't use a gain too high and or too low. It's got that sweet spot there. So when you're doing an amplifier, amplifying current, the gain's really important, the gain you choose, even voltage. Okay, here we go. So let's take a look at the gain and find out what we're going to choose. I'm going to choose 250 and 280 and maybe work with both of them. Okay, so step one, when you've got any kind of BJT circuit, you have to calculate the current going through the collector. Okay, in this case, we know that the current going through the collector is also the current going through the load. So when I want to calculate this, I know it's going to be the voltage drop across the load, which is VCC minus VCE, and then divided by the resistance of the load. So in this case, we've got 60 minus 0.3 volts divided by 150 ohms, and I've got it's not 1, it's 389, 398, 98 milliamps. Okay, so whatever, less than half an amp, not a lot of current. So we know that that's what we're after. So my step two is going to be calculate my IB, and this is where the gain comes in. So let's just go for 250. So my IB is going to be my IC divided by my gain, and in this case, my IC is going to be 398 milliamps divided by B, which is 250. Now, for 250, I've got these values over here. For 250, 1.4. So I need 1.4 milliamps to fully saturate this when the gain's 250. So now let's do this calculation again. And let's calculate IB at 280. Okay, so when my beta is 280, so I've got my IB equals, in this case, it's 298 milliamps divided by 280. In this case, I have 1.58 milliamps. Okay, good. So a little bit more, not a whole heck of a lot more. So now what I need to do from there, essentially step three, I need to calculate my RB. So I'm going to calculate my RB, and I'll just go with this gain. I'll go with the gain of 250 first. So at 250, at B equals 250, my gain is going to be, now this is all about the voltage drop across this guy. So my RB is going to be my voltage drop across this guy, which is BB minus VBE. Okay, the voltage drop across that is going to be my voltage here, right, which is essentially, I've got VA here on the board. I should actually be writing that in my formula. VA minus VBE. Now my VBE in this case is 0.7 volts. You can get that from the data sheet. Okay, good. So divided by my current, and I'm going to go with 250, I need my 1.4. So 1.4 milliamps. And in this case, I've got, what did I get? I got 27.2, no, I got that wrong. 2.72 kilo ohms, 2.72 kilo ohms. So I'm going to see what kind of resistor I need for my gain of 280. So when B equals 280, then I'm going to choose my resistance. So in this case, I've got a different current when my gain was calculated 280. So my RB is going to be, now let me actually put these numbers in this time. So I'm going to say that 5 volts minus 0.7 volts divided by the current is going to be 1.58. 1.58 milliamps. That's not very good. 8. So let me just pause here and stop and tell you about why this is 5. Check it out. If I were to turn this V, that should be VA. Yes, I got that VA. Right. When I turn this all the way down, that resistance is 0. What's going on is actually we're going to see 5 volts at VA because that'll be the full voltage drop across this 410. So I'm going to see 5 volts there. Okay, let's continue on. So in this case, I've got a resistance here of 3.03 kilo ohms. So if I use a gain of 250, that is what I've calculated to give me the current. If I use a gain of 280, that is what I've calculated to give me the right current to saturate this thing. Okay, so as we know, we got to go a little bit lower. We calculate the amount of resistance to saturate the BJT, and then we go lower. And as a switch, we just might as well just go by half. Well, double the current and lower the resistance by half. or something like that. But in this case, we can't do that too much because we want to get as much out of this and as much out of this as we can because we're actually controlling the current. So we're actually bringing the current down. We want to bring it up to the actual, we want to bring the current up here to the saturation, maybe a little bit more. But if we brought it way up here, then we're losing a lot of control. Okay, good. So what we're going to do is we're going to take a look at the different resistances and how much actual current we've got going through here and what's going on. So over here, I've got a bunch of different resistances. So I'm choosing, in this case, I've got 2700 and 3. So I'm just going to go with a 29. If I actually used a 2900, then I'm going to get 1.48 milliamps in here. And 1.84 milliamps is pretty good. Because I need, if the gain is 250, I need at least 1.4. So if the gain, if the transistor did cool down and it was actually 25, and I cranked this up, and I had as much voltage as I could going through here, and I used a 2900, then this wouldn't be saturated. It would still be, there wouldn't be a full amount of current going through that. So I'm thinking 29 isn't going to cut it. Let's go down a little bit. 27. If I used a 2700 ohm resistor, then my current is going to be 1.57. So here we go. Oh, look at that. If my gain snuck up to 280, because it warmed up a little bit, my gain snuck up to 280, and I used a 2700, and I turned this all the way down, this current would be at maximum, and you know what? That would be saturated, and the light would be on, because I need 1.58 milliamps to saturate it at a gain of 280. So that's going to work. Let's just kind of take a look. Let's say it cools down a little bit, goes to 25, maybe right at the start, as soon as I turn it on, right? It's not hot. Okay, then I need 1.48 milliamps to saturate it. If I use a 2700, I've got 1.57. So if this is my saturation level right here, I'm actually going to go up to here a little bit. And if this is my range, then this area here, as I turn that pot, I'm actually sneaking up all the way up to here. So I'm actually losing a little bit of control with the pot. But it's not so bad. So I'm thinking 27 is pretty good because probably this thing, as it gets warm, it's going to be more than 25. But because I have cooling on it, it's not going to go more than 280. So your best bet is to actually use a 2700 ohm resistor for your base, and then you'll be in that sweet spot where you'll be able to control this really well. Okay, I want to just go on a little bit more about what's happening here, but essentially you've got what you need to be able to do this assignment. So you want to stick around with me for a bit. I'll talk about how this works and why I designed it like that. Okay, cool. Oh no, I erased that stuff. I shouldn't have erased it. I didn't erase it, but I almost erased it. Well, this is a dirty whiteboard. It's one of these whiteboards that you stick on the wall. They don't clean very well. Okay, here we go. So, why did I choose these values? Well, I'll tell you about the 410 and the 2500. Cool. Let's just say that I turn this all the way down. Turn it to 0. What I want is I want as much range out of this as I can get. So I want to be able to, if I turn it a little bit, just a little bit, that like from 0, if I turn it just a little bit up, I want the light to come on, right? So what I've done here is I've put a 410 here. And what that means is that essentially, just pause for a sec. I could just get rid of this thing and I could connect that right to my wiper. And then I'd still actually be pretty good. But what I've done is I put a 410 here because just take a look at this. If I were to dial this all the way up, so that if I went counterclockwise, this would go all the way up, then I've got 2500 from here to here. And then I've got 400 here. So my voltage drop across here is going to be, let's take a look at it, 410, right? Okay, good. So if I dial this thing all the way to 2500, if I dial all the way to the left, what I'm going to get is, I'm going to get this VA is actually going to be 0.704. So it's just going to not saturate. It's just barely going to allow current to then go through there. So that light is probably not even going to show that it's coming on. But if I didn't put that there, I've got a little bit of turning on the potentiometer that I'm not going to be using. So I want to start with my pot all the way to the left. I want to start at 0.7. And you'll probably just put a switch in here to be able to turn the thing on and off as well. You can actually use the switch on the pot. So if you wanted to turn the light off completely, just turn it all the way and click the switch will open. But as soon as you go clockwise a little bit, the switch closes and you have current. So as soon as the switch closes, I've actually got some current running through here. It's a very small amount of current, but it's fine. Now, as I turn that more clockwise and more clockwise, what's going to happen is this guy is going to get lower and lower and lower. And if we actually do the math over here, so my V, right there, my V maximum, the minimum, that should be minimum. That actually should say minimum. No, it should say max. That's right. As I turn this to the right, what's going to happen is that this will slowly become 0. And then my VA is going to equal my 5 volts out. So as I turn that to the right, sorry about the lighting, that's going to go that way, and then I'm going to get as much current, the maximum amount of current through here, because that's going to be at 5 volts. But as I turn it all the way to the left, I'm still going to get 0.7 volts, or just a little bit more than 0.7 volts. So I'm going to have just the smallest amount of current. So that's why I chose these values, and that's why you'll put a pot there. If this was some kind of sensor that changed its value because of some physical property, pressure or temperature or force or something, then you could do the same thing. Now you may want to put that here and put that up there, but that's how you balance all of these things. What else do I got to say? You think we're good?